Hello students. In this tutorial, we're going to be looking at the current divider rule. We'll start by deriving the rule, and then after that, we're going to move on to look at an example on how we actually use the rule to work out questions. Now, the current divider rule is used to determine the current that we pass in a resistor if the resistors are connected in parallel. This is because in a series connection, we know to say the current that comes from the source, if the current coming from the source is I, that same current will pass through the first resistor, and it will be the same current that will come to pass into or through the second resistor R2. So in a series connection, the current in the line will be the same passing through all the resistors. So it will be the same as I. But if resistors are connected in parallel, let's say from the source you have a current coming, let's say I, sometimes to be labeled as I in to mean the current being fed into the circuit. So that current, as it approaches this junction, we can even use Kirchhoff's law here to say that at this node, the current has to be equal. The current entering has to be equal to the current leaving. So the current from the source enters this junction, and then it will split up. Part of the current will go through this line, while part will take that route. So if this current coming down here is taken as I1, and the current going that side is taken as I2, then if we wanted to determine what I1 is, because that's the current passing through R1, then we'd have to use the current divider rule. So the current divider rule is used to determine the current that will pass through any resistor in a circuit, provided the resistors are connected in parallel. Now, what is this current divider rule, and how can we actually come up with it? So the first part, I will derive that expression for you, and then after that, I'll show you just how to use that expression. So let's see, where does it come from, and how do we use it? Well, the first thing that I'd want you to first look at is how do we actually get the current coming from the source. Sometimes it will be given to you, but sometimes you might have to calculate it. They might give you the voltage being supplied to this circuit, but then we need to find the current in this circuit. Now the current that will be coming from the source, we know what we have to do. The first thing is to determine the equivalent resistance in our circuit. So that will be the first step. So let's find the equivalent resistance in our circuit, because we know to say the current from the source is going to be related to the voltage that is being supplied to this to be equal to the current multiplying the equivalent resistance. So this is what we're going to have. So if we wanted to find the current coming from the source, all we would need, this current will be equal to the voltage supplied to this circuit divided by the equivalent resistance of our circuit. This will be the current I that is coming from our source in this case. So now in this way, suppose we wanted to find the current that is going to come down towards R1. So if we wanted to find the current coming down towards R1, so let's say wanted to find the current I1, we know to say the current I1 from Ohm's law again, V is equals to IR. So from Ohm's law, we know to say I1 is equal to the voltage that I1 is seeing divided by the resistance of R1. So with this in mind, so from Ohm's law we have this relationship. The next part is to just plug in a few things. And the thing that we want to plug in first is this voltage V1. Well, what you have to observe is for parallel connection, the potential drop that we'll be seeing will be the same. In this case, the potential drop that will be observed by R1 and R2 will be the same as V coming from the source. So resistors in parallel will see the same potential, or the potential drop across them will be the same. In this case, it will be the same potential that will be coming from the source. So it's the same V. I might as well, instead of writing as V1, I might as well just write as V over R1. So since this is V, remember what V is. From the first part, we had from Ohm's law, the voltage from the source is equal to the current multiplying the equivalent resistance. So this is the expression for the voltage coming from the source. So we can get this and plug it here where we have V. So our expression for the current passing through R1 is now equal to the current coming from the source multiplying the equivalent resistance, then divided by the resistance of R1. So this becomes an expression that you can use, the equivalent resistance divided by R1 multiplying the current coming from the source. Well, this is one version of the current divider rule. This can work especially in an event where you have more than two resistors that are parallel to each other. You might want to use this version of the current divider rule. But what if you know what the equivalent resistance is? Let's say you have just two resistors that are parallel to each other, like demonstrated here. So if you have just two resistors, how do we then use that current divider rule? Or how will it actually look like? Well, if there are two resistors, which of course will be the case for most examples that we're going to have, even the ones which don't have two, which have more than two, we'll tend to simplify them so that we're only looking at two. So if we have two resistors just like this, we know to say for two resistors, the equivalent resistance will just be given by R1 times R2 divided by R1 plus R2. So this would be the expression for the equivalent resistance. We saw earlier to say the current passing through R1 will be given by this expression. Sorry, this is R1 here, based on that. Yeah, that's R1. So we know to say the current passing through I1 will be given, the current passing through R1 will be given by this expression. So where there is R equivalent, we can put the expression for the equivalent resistance in this case. So we have I1 being equal to the equivalent resistance divided by R1 multiplying the current coming from the source. So in this case, the equivalent resistance, so I can say we have the equivalent resistance, that's R1, R2 divided by, so the R1 first coming from here, then that R1 plus R2 coming from the equivalent resistance. So I hope you guys were able to follow through this, but basically if I was to do it maybe a little bit slow, so where there is equivalent resistance, I would have R1, R2 divided by R1 plus R2, then this all divided by R1, then of course it's multiplying I. Focusing only on this, making it a single fraction, we end up with R1, R2 divided by R1, and then we have R1 plus R2, then it's multiplying the current coming from the source. R1 and R1 will divide out, leaving us only with the current coming from, the current passing through R1 being equal to the resistance of R2 divided by R1 plus R2, then multiplying the total current coming from the source. So this becomes the current divider rule that we'll be using for the most part. Now, this is the current divider rule, but how do you use it? Because in most cases you don't really want to derive it, you just want to use it. Now, how does it really work? How do you use the current divider rule? So let me show you a trick on what you just have to look out for. So let's start from that diagram. So we have this. So to find I1, if you have two resistors, even if it's not two resistors, if you have three, of course, this meaning this here will just be taken as the equivalent resistance of the other two that will follow there. But if you wanted to find the current passing through, let's say I2. So if you wanted to find the current passing through R2 here, so the current passing through that, if you're finding the current passing through this, then what will be in the numerator will be R1. So this will be R1 divided by the sum of the two resistors, which is going to be R1 plus R2, then multiplied by the current coming from the source. So this is the current divider rule to determine the current passing through R2. If you wanted to find the current passing through 1, it will mean that the resistor that will be on top will be the other resistor. Since this is through 1, this will be R2, and then of course the sum, R1 plus R2 multiplying I. So generally this is the current divider rule. Now with this, let's look at one simple example before we just mention one more thing. Let's look at this example. In this example, we want to determine what I1, I2, and I3, what they are. So let's look at the circuit that we've been given. So this is the circuit. we have a 30-volt power source. R1 is 10 ohms. R2 is 30 ohms. R3 is 50 ohms. So I1, of course, is the current going in this line. I2 is the current going in this line. And I3 is the current going in this line. Now, how do we find them? Well, there are two methods. Now, let's see how it goes. Well, for the first part, since we're given the voltage, we need to know the current that is coming from the source. So to find the current coming from the source, we need to get the equivalent resistance of our circuit. So of course, we can do this in step. I prefer the step method. So first I'll combine R2 and R3. I'll take them to be parallel to each other. So let's see what I'll have for R. So I'll say RT1. I'm combining R2 and R3. I'll say their product. Then their sum. So of course from here, R2 is 30. R3 is 50. Then their sum, 50 plus 30 is 80. So from here, we get the total resistance here as 18.75 ohms. So what this gives us is a combination of R2 and R3 and R1 still here. So R1 was 10 ohms and RT1 is 18.75 ohms. So of course we can then combine these two. So we can get our total altogether. And this will be the product 10 by 18.75, then the sum. So if we do the math here, this comes to give us the total resistance of our circuit as 6.52 ohms. Now we can use this value to determine the current that is being drawn from our source. We know to say voltage is equal to IR from Ohm's law, so that the current coming from the source will be the voltage divided by the total resistance. So the voltage from the source is, what's the value again? That's, let's see the value. So that's 30 volts. So we have 30 volts divided by the equivalent resistance, which is 6.52 ohms. So we get the current coming from the source as 4.60 amps. So this is the current coming from the source. Now, how do we determine the current going through I1, I2, and R, and the current going through R1, R2, and R3? Well, there are two methods we can use here. For starters, we can start with this circuit where we had combined R2 and R3. So I can use this to say they are parallel, and then we want to determine the current going through this side, which is I1. And then, of course, the rest will be going towards the combination of R2 and R3. So to determine the current going towards the 10 ohm resistor in this case, remember how it goes? So if we wanted to find I1, so in this case, it's, since I1 is where we're going, R1, that we're going towards the 10 ohm. So what will be in the numerator is the other resistor, which is that 18.75. That will be in the numerator. So we're going to have that 18.75 divided by the sum, which is our R1, which is 10, plus the other resistor, 18.75. Then we'll multiply this by the current coming from the source, the current entering that junction, which is 4.6. So if we do the math here, this comes to give us I1 as 3 amps. After obtaining this, the rest, see, what happens in terms of current is when you reach a junction, the current entering is 4.6. Part of it goes towards 10, and we've just seen that what goes towards 10 is 3 amps. The rest has to start going towards that 18, and the rest, if we less 3 from 4.6, what remains is 1.6. So only 1.6 amps actually goes towards that combination of R2 and R3. Now they will be sharing that 1.6. So if I wanted to get I2 and R3 using this method, it's the 1.6 I'll be dealing with. So I'll write this only showing R2 and R3. So let's say this is the current coming from that point. So that 1.6 that was left, it's approaching R2 and R3. So in this case, to find I2, notice that what they'll be sharing is that 1.6. So the current entering the junction is 1.6. I2 will be equal to the other resistor. Since I'm finding I2, the other resistor is R3. So it will be R3 divided by the sum R2 plus R3, multiplying the current entering that junction, the current the two are actually receiving, which is 1.6 amps. So from here, we know what R3 is, that's 50. R2, what's the value for R2? That's 30. So we have 30 plus 50 multiplying 1.6 amps. In this case, the value comes out as 1 amp. So if R2 gets 1 amp and what was coming was 1.6, then the rest goes towards R3. You can try to do the math, but since you only have two resistors, to find R3, it will have to be R2 divided by R2 plus R3, then multiplying that 1.6 to. This math is going to give you 0.6, which makes sense if you follow Kirchhoff's junction law. So this leaves I3 as 0.6 amps. Now, there is another method that we could have used here to get the same values. Remember what we did earlier on. Earlier on, when we were deriving the current divider rule, we sought to say that the current going towards, of course, we did this for only two resistors. We sought to say the current going towards the first resistor is equal to V1, the voltage across that resistor, divided by the resistance of that resistor. But then we sought to say, since these resistors are parallel to each other, the voltage here is the same as just V, which left us with just V divided by R1, where V was from the source. And from Ohm's law, we had V is equals to I R, where R is the equivalent resistance. This led us into having the current entering, coming from the source, the equivalent resistance, and then R1. So this was another expression of the current divider rule that we had, R equivalent over R1 multiplying the current entering altogether. So we could have also used this approach to actually get the current across each resistor, having calculated the equivalent resistance. So remember the equivalent resistance for the entire circuit, we found that as 6.52 ohms. So let's say you wanted to find the current across that 1 ohm, or passing through that R1. So R1 was 10 ohms. The equivalent resistance is 6.52. R1 is 10 ohms. We're multiplying this by the current from the source, which is 4.6. Doing this, notice that you are going to get 3 amps still. So you're going to get maybe 2 point something and so on, but all in all, this is going to come back to 3 amps. We can do the same thing for I2. For I2, again, the equivalent resistance in our circuit is still 6.52, but the difference is the resistance for I2. Remember the formula? This is I1 is equals to the equivalent over R1 itself. So if you're finding I2, it's going to be the equivalent over R2. So this is I2 6.52 over R2, and R2 is 30. So multiply this by the current from the source, which is 4.6. Doing this will give us 2.999 and so on. To give us no, that's for I1. That's one that gives us 2.99. For I2, we're going to get this will be 0.999 and so on. So this can be rounded off to just 1 amp. So same way we can find I3. Again, you're going to have that the equivalent resistance, that's 6.52 divided by the resistance of I3, the resistance of R3, which is going to be that 50. That's the 50 ohms. Then multiplying the current again, 4.6. So we see that when we do this, we're going to get 0.59984. So again, when we round off this comes to give us 0.6 amps. which are the same values that we got using the earlier method. Now, I don't know if you guys have noticed. Look at one thing here. R1 was 10 ohms. And the current passing through R1, we ended up finding the current there as 3 amps. R2 was 30 ohms. The current passing through that, we found 1 amp. And R3 was 50 ohms. And the current passing through it, we found that as 0.6 amps. Now, notice one thing here. The current that passes through a resistor depends on the resistance. If you have resistors that are in parallel, current tends to take the route that is easiest to pass. The resistance is the measure of difficulty in a route or in a line. So the larger the resistance, the more difficult it will be for current to pass in that line. Picture this. R3 here has the largest resistance of 50 at 50 ohms, implying that that line is the most difficult to take. That route will be very hard to take. Because of that, less current tends to take that route. R1, however, has the smallest resistance. Because of that, more current tends to easily take that route as compared to R2 and R3. So it's one thing that you just want to keep in your mind. More current will pass in a route that is easier to pass. So if you had, let's say, a line like this, where you have maybe somewhere here, you have a resistor. Let's say this is a 30 ohm resistor. And then this side you have nothing. And then you have your power source here. And then let's say, yeah, our power source is this side. So as current comes from this direction, it reaches this junction. If we argue, of course, every line that you can connect will have some resistance. But if we argue to say that the resistance across this is nothing, while the other side we have a 30, what you should see is that this route is very easy to take. So as current comes through this route, we expect literally everything will take the easier route. Nothing will go towards the 30 ohm resistor. So in other words, we argue to say that the 30 ohm resistor has been shorted out from this circuit. Why? Because there is an easier route to take. Current is deciding to take that easier route, and nothing tends to go towards that 30 ohm. We can literally do the math to show to say that no current will go towards the 30 ohm using the current divider rule. But here I just wanted to point out to say current will take the easiest route in any circuit. Okay. Now, guys, that brings us to the end of the current divider rule. We'll try to find more examples to work out, but most questions, I think most application of this will be combined with other ideas. So look out for stages where we have to use this method. So in the next tutorial, we're going to see the voltage divider rule and how to use it. Now, guys, we'll see you in the next tutorial.